Okay, guys, how you doing again? Jim Malus here. Let's keep talking a little bit about certain things. In this particular discussion, I'd like to talk a little bit more about thermodynamics. And basically what I have written up here, an intuitive look at E sub TH equals 3/2 nRT. We talk about the internal energy U. In some of the literature, the U for internal energy of a gas in a container, the internal energy gas in a container, internal energy in general U is often written as ETH. So internal energy, you can see it written as U, you can see it written as ETH. ETH is maybe a little more intuitive to look at, though you don't always see it in the literature. You see it both ways depending what literature you're looking at. So we're talking about the internal energy of an ideal gas. The internal energy of an ideal monatomic gas is ETH equals 3/2 nRT. So we're going to take an intuitive look as to why that's actually true. Why is it E sub TH equals 3/2 nRT? Well, we've already answered it. I guess I'm rephrasing stuff that's already been discussed in some of the brilliant work of numerous great physicists and numerous great educators pertaining to physics, numerous great science educators, mathematics educators, physics educators. So I say here in some of the writing I have, and I have this posted on Canvas for you, once again drawing from the brilliant work of Surway and Buell, College Physics, 11th edition, volume 1, pages 332 to 342. So Surway and Buell, we see a lot of this stuff, guys. We kind of write that over here and then erase it. But basically we're getting this from the Surway, or at least we're getting a lot of this. It's not the only place we can get this, certainly. There's other places that talk about it. But Surway and Buell, and that's their book was College Physics, 11th edition, volume 1. And the pages we were talking about, and again, it pertains to this. We already said that, and this is really the big thing here we're talking about. Much of their brilliant work about which we're speaking right now, and from whom we're citing, is going to be found on these pages of Surway and Buell, College Physics, 11th edition, volume 1. So we've got this right here pertaining to that. And like I said, I say a couple things here, and I'm sure that much, if not all, of what I'm saying has already been discussed by others. Essentially, Surway and Buell basically does it. They don't quite say it in the way I'm about to say it. I can't remember if I've seen it said in the way I'm about to say it. I'm sure I've seen it. I'm just forgetting it, or I'm certainly sure it's out there. It's pretty basic stuff, and at the same time, it's I think some very interesting conclusions that we would see. And like I said, I'm sure it's out there, and I think it's just something we need to bring to our attention. From our previous discussions in and pertaining to the kinetic theory of gases, now we did have, maybe you remember guys, there was a kind of a long discussion that I have not only online in Canvas as far as in a written form, but we also talk about it in the videos as well in different places. There's discussion regarding what's happened here. So we do talk about it. We know that the ideal gas law holds and is applicable in very many circumstances. That ideal gas law is very profound. And like I said, there is a discussion I brought up earlier that we kind of, rather than redo the whole discussion, we can look it up in the literature that I have on there in Canvas, where I've drawn from brilliant scholars, and I was able to just put it down there. And also some of the discussion I gave about this already. We've already done this work elsewhere where we're actually deriving something. We're actually deriving this. we're getting this answer, and then we do other stuff to talk about how does this derivation of a gas having 3 degrees of freedom, which namely is an ideal monatomic gas and has 3 degrees of freedom, this is its total internal energy given this absolute value temperature. Notice the only variable, well, n's a variable too. If you hold n constant, everything hinges on the average kinetic energy of the particles in the gas. Well, the average kinetic energy is directly proportional to the absolute value temperature. Large absolute value temperature is associated with great kinetic energy on average. The average kinetic energy of the particles, the average kinetic energy of each particle is very great if the absolute value temperature is very great. If the absolute value temperature gets cut in half, made smaller, gets cut in half specifically, then the average, if the absolute value temperature gets cut in half, the average kinetic energy gets cut in half per particle, on average. Okay, so it's pretty important stuff. This absolute value of T is profoundly significant when we're talking about gases and talking about their internal energy. So, left that out there, left that hanging out here, guys. This word "the," let's talk about what "the" is associated with. The kinetic theory of gases. And as I said, this is something, I gave it this title, not that I needed to give it this title, other people have given it this title as well. I've associated this title and I've written about it in Canvas for you guys, and I've also talked about it on film. So much of what we're going to see here, we've already seen in writing on Canvas, and we've also seen it on film, following very closely to that which we have already seen, you guys. So, regarding that. So, what we got here, guys, make that a little bit easier to look at. Okay, so we're looking at that to always come back here. Well, as we say that, we know that the ideal gas law holds and is applicable in very many circumstances. So let's, again, we're not going to redo stuff we've already done, but let's at least go back to some of what we've already done and see what we can say. Okay, guys, I've got different things I can use here as well. Excuse me. There we go. Okay, so let's take a look, as we've said, and we'll erase wherever we feel we need to erase. We don't have the greatest amount of room, but it sure could be a whole lot worse. Pretty good setup to this thing, guys. As always, when you're doing this stuff, go ahead, go back. I mean, that's the one advantage to having this on film, I guess. You can always speed it up if you're familiar with what I'm doing and stuff. So we'll see where we can take it. As we talk about this, as we said, we know that the ideal gas law holds and is applicable in very many circumstances. What are they talking about? Well, let's make it very clear. That's something experimentally confirmed in the right circumstances. In many, many circumstances, to a large degree, there's a lot of validity to it. If not exactly the case, very close to being the case. It's a very good approximation, at the very least, in very many circumstances. It holds. By and large, it can tell us a whole lot. PV equals nRT, and we've already talked about that when we talked about the ideal gas law. And this is something when we're talking about moles. If you want to expand this and talk about the actual number of particles that are moving, You could write it like this. So one's born of the other. They both mean the same thing. A lot of pressure times a lot of volume is a big number. How do you get a big number like that? Well, if that's a constant, the only way you're going to get a big number, comparatively speaking, is a lot of particles and a lot of temperature, a lot of average kinetic energy per particle. If there's a very, very big temperature, which is an indication of a large kinetic energy per particle on average. And this right here is a large number of particles. Many particles, and all of them on average moving very fast, there's going to be a lot of pressure and a lot of volume. Sure, it's easy to get a lot of pressure if you don't have a big volume. This is saying you got to, sure. I mean, if you can have a big volume, and if you get a big volume, the pressure goes down. Yeah, we understand that. Now, if you want a big pressure, you push it down, you make a small volume. So pressure could be very big, but V could be very small. Or let it expand, and V could be very small, and pressure could be very big, and then you compress it enough. Well, there's a small volume, but a big pressure. Or you let it expand, there's a big volume and a small pressure. What if they're both real big? Man, the only way that can happen, among other circumstances, a lot of particles and a lot of average kinetic energy per particle, which is an indication of the absolute value temperature. The absolute value temperature is a great measure of the average kinetic energy of particles. That's the same argument here. N is number of moles. That's the same as saying a lot of particles. A lot of moles means a lot of particles. It's very similar to saying this. T is, again, T and T are the same right here. So it's the same kind of argument, you guys. All right, you've seen me have this discussion in other places where I try to talk about thermodynamics. We've already seen the kinetic theory of gases. I discussed that on film and in writing, so we can find both on Canvas for our class. And we've just seen a lot of this stuff discussed, guys. So we got it to here. They basically just kind of say, kind of keep it in the back of your mind, if you got PV equals nRT, and you got the other one, like I said, we wrote them down there. You got this. Is it true? Well, is the number of particles divided by Avogadro's number, is that the number of moles? Yeah, it sure is. Well, Avogadro's number and R are two constants, so why don't you just leave the big N, number of particles, alone, and take R, universal gas constant, and Avogadro's number, have them right there like that, times T, and they call this, a constant divided by another constant is still a constant. A constant divided by another constant is a constant, and that's where you're getting this. And that's, at the end of the day, that's where they were saying something like this. Now, we, again, don't want to keep saying this to you guys, drive you nuts about it, but we've already discussed all of this. So what's the point? Well, observe, we recall from the kinetic theory of gases and the discussion pertaining to it, the conclusion, we had actually reached the conclusion, guys, when we were doing this stuff, from all of this, we said that the total kinetic energy, if you could somehow add all those kinetic energies together of all those particles, doesn't matter that they're all moving randomly. In fact, about a third of them are moving sideways associated with the x-coordinate. Another third are, on average, moving sideways associated with the y-coordinate, and another third are moving up and down associated with the z-coordinate. Roughly, at any given moment, about a third of the particles are associated with what's going on, with collisions going on, associated with the x, I don't want to say direction, the x-coordinate, I guess you'd say. X direction goes back, and there's two x directions, right? I guess you could say there's one in the positive x direction, one in the negative x direction. Sure, fine. But everything associated with the x-axis, a third of the particles at any given moment, on average, are moving in the are moving associated with the x-coordinate. A third are moving associated with the y-coordinate, and a third are moving associated with the z-coordinate. Or another way you could put it is, all the particles are moving, but 1/3 of their total kinetic energy is associated with the x-axis, another third associated with the y-axis, and the last third, so to speak, or the third of the kinetic energy, another third of the kinetic energy, the last third of the kinetic energy is associated with the z-axis. So, that's interesting. We'll come back to that. Ke total. All right, my chalk's not cooperating too well with me today, but let's, we're going to get through it. All right, we got this, which is the same as this. Well, that's pretty significant. Yeah, I mean, the fact, you're seeing the same thing over again. That's true. Okay, sure. So what does this mean? It means a lot of stuff. I mean, this total Ke, this Ke total. I mean, again, forgive the redundancy on this stuff, you guys, but the Ke total in association with what's going on with this whole thing, there's 3/2 nRT is equal to the ETH conclusion that we had drawn earlier when we had that kinetic theory of gases discussion at an earlier time that we talked about, or at another time, depending on what order you're looking at these videos, you guys. But you're saying ETH is 3/2 nRT. It's the same thing. Yeah. The total Ke, as we look at this, the total Ke and the ETH, yeah, they're the same for our purposes there when we're looking at this. So, okay. All right, interesting in its own right. They are equal for a monatomic ideal gas. And generally, when we do all that, we're generally going to find something else. In a very general sense. By the equal partition of energy principle, by the principle of equal partition of energy, the number of degrees of freedom associated with the gas in whatever circumstances in which it is found, the number of degrees of freedom of the gas given the circumstance, degrees of freedom of gas could change depending upon the circumstances. Depending upon the kinetic energy that's being imparted to the particles, how many degrees of freedom are showing up. That could be the case in some circumstances at least. For our purposes, let's just say this. According to the equal partition of energy, according to the equal partition of energy principle, all the degrees of freedom share the energy that is the internal energy of the gas. They share it equally. However much internal energy is associated with the vibrational process, the oscillations that take place that way are the same as the rotational in one way that's rotating, the same as the other way in which they could be rotating, and the same as 1 degree of freedom moving back and forth on the x-axis. And that's going to be the same as the amount of energy partitioned associated with the y-axis. And all those, so each one of them are equal amount of energy. Each degree of freedom has an equal amount of energy associated with it for the circumstances in which that gas is found. The degrees of freedom, the number of degrees of freedom divided by 2 times nRT will give you ETH. So let me Probably went more than I needed to go here, guys, but whatever. That's kind of interesting. How many degrees of freedom are there in an ideal monatomic gas? There's 3. It is an equal amount of energy partitioned. It's an equal amount of kinetic energy partitioned associated with the x-axis. The amount of energy partitioned associated with the x-axis, that degree of freedom, is equal to the amount of energy associated with the y-axis, and each one of those is equal to the amount of energy associated with the kinetic energy associated with the z-axis. These are all kinetic energies we're talking about, and in each one of those degrees of freedom associated with the x-axis, associated with the y-axis, associated with the z-axis, each one of them has an energy. I don't want to say there's a partition of the total kinetic energy associated with the x-axis, which is equal to the partition of kinetic energy associated with the y-axis, which is equal to the partition of kinetic energy associated with the z-axis. There's 3 degrees of freedom. Really? 3 degrees of freedom. 3 degrees of freedom over 2. 3 over 2 times nRT. ETH equals 3/2 nRT. What if there are 5 degrees of freedom? 7 degrees of freedom? 7 degrees of freedom, okay. Each one of those 7 degrees of freedom has 1/2 nRT. Each one of these 3 degrees of freedom had 1/2 nRT. It's like that 1/2 nRT plays a big role. Multiply 1/2 nRT by 3, you get 3/2 nRT. All right, well, there's something interesting here, I think. Let us consider a cylinder or some other container that initially has no volume. Let's make this kind of an interesting math problem, kind of a thought experiment, but let's just see hypothetically, does it make any sense to us? Can we sort of get an intuitive feeling for what is going on here? That's the goal, right? Well, I'm asking this. I'm saying let us consider a cylinder or some other container that initially has no volume but has a piston, some sort of piston, that allows it to attain any volume as we increase the average kinetic energy of the ideal monatomic gas. The more average kinetic energy I can put inside that monatomic gas, the piston's going to tend to move upward. The volume's going to tend to expand. Well, yeah, but if it's an infinitely light piston, it's going to move anyway with the slightest thing. Okay, I'll tell you what I'm going to do. I'm going to attach a spring somehow to the piston at the very, very bottom where there's no volume. But there's still n number of moles of gas present, but they're all compressed down to nothing or close to nothing. For this little thought experiment. They're compressed down to nothing or close to nothing, and I'm going to heat that thing up. I'm going to give kinetic energy to the particles, and that's going to expand the piston. There is a spring tied to this thing. Well, springs behave in a very, I don't want to say odd way, in a very interesting way. Let's talk about it. What allows it to attain any volume, let's say theoretically, as we increase the average KE of the ideal monatomic gas. See exactly how you want to do this. Like the way I wrote it may have been a little more wordy than I wanted to make it when I did an actual writing. So let me, perhaps I don't need to say a whole lot here, guys, on this. But let's just see. Okay, we've got a lot here. I guess I could say for sure you're going to see this again. We're going to see this again, and we'll take it from there, how that's actually going to play out. So let's see here. Let's derive a few things and see what we can say. All right. Well, we already knew a couple things. Now I'm erasing the things that we already kind of knew. We knew that from the discussion of the kinetic theory of gases, how they were able to derive that for an ideal monatomic gas, the internal energy, E sub TH, was 3/2 nRT. I just want to kind of look at it in a little different manner, maybe we can kind of see that there's some fascinating things that can be said, I think. Not really complicated, doesn't take long, but fascinating nonetheless, I believe. Okay. Forgive me here, guys. I just need to make sure I got. Okay. So we talk about a bunch of things here, guys. I guess you could say, you know, we based on what I'm saying, guys, we're saying that at V equals 0, there's no stretch. T equals 0 then. And we're always dealing with absolute 0. There's got to be, I mean, you can do the physics with any sort of absolute 0 temperature scale that you want, but it's got to be an absolute 0 temperature scale. You can make up an absolute 0 temperature scale, and you can do all of the physics, all the mathematics, but you got to be consistent on how you talk about it, and you got to be able to, to formulate units and stuff like that. But that's okay. What you cannot do is have the quote-unquote units we're used to seeing, Fahrenheit or Celsius or something like that. So, that having been said, an absolute value temperature scale is absolutely essential, and we'll use the one that's been with us forever. The Kelvin temperature scale, T equals 0 means absolute 0. Have no doubt in your mind about that. That's absolute 0 that they're talking about. Okay? And as T increases, that implies V increases. Makes sense to me. It's just not going to spontaneously do it because there is a spring on this thing. The spring's not going to let it move unless this thing earns its money. Unless this thing earns its keep, there's not going to be any expansion. Now, if there wasn't a spring and the piston were something infinitely light, so to speak, and there was no force to be overcome here, it's like floating in outer space for that line of thinking, I guess you could say. But it's not the way it is. There is going to be something attached to it. So, okay, I said a bunch of things here on this. As we said, we're going to attach the ideal spring. There's going to be some stretch associated with it. We note that the continuous increase in T from T equals 0, absolute temperature scale, to any value of T that we choose, corresponds to work being done on the spring. And at any height, D, we have, what do you have? Well, what do we remember about springs, you guys, in general? I mean, we say, I know we said negative kx. I don't want to go there. I do want to go there. It's true. It works. Absolutely. Let's just talk about magnitude. The spring is going to pull back when you pull on it. If you don't pull on it, it's got no pull. If it's not stretched at all, it's really got no pull because you've not done anything to it. The more you pull it, the stronger it pulls back on you. It's an ideal spring. You can never stretch it so much that it's not going to come back. It's an ideal spring, so you can stretch it as much as you want, but as much as you want to stretch it, the more out you go, the stronger it's pulling back. It's always resisting. It's always trying to get back to equilibrium. That's where the negative comes in. Well, that's true. That's absolutely true. In terms of magnitude, it's kx. K is the spring constant, a constant. X is the amount of stretch. The more stretch you got, the more that thing is pulling back on you to try to get back to where it was, to an equilibrium position. So you pull it out quite a bit, pull it way, way out there, it is really pulling hard to get back. Interesting. What does that mean? Well, that means it's hard for you to pull it out there. For you to pull the spring out that way, for you to pull the spring very far out, there's going to be a lot of force at the very end of that pull, no force at the beginning of the pull, but on average, it had to be a lot of force to do it. Didn't we say that work equals force times distance? Tell you what I'm going to do. Do a bunch of things here, and we can change the symbols and stuff like that, but I'll tell you what I'm going to do. For the spring, let's take the average force that you would have to exert on this thing and take it out over a distance x, let's say. And that'd be the work that you did. Well, okay, yeah, big deal. What's that? What is the average force? We talk about it a bunch of ways. The average force is, there's a lot here. Because of the nature of the function, because of the nature of this function right here, this is a linear equation. What's the average value of the linear equation between two different values of x? I would add the value at x1, I'd add the value at x2, after I added them, I'd divide by 2. I'd get the average, the straight out average. I'd average what the force was at x1, I'd average what the force was at x2. It got stretched from x1 to x2. I'd average kx1, that's the amount of force at that point, and then kx2 is at the other point, add them together and divide by 2. Tell you what I'm going to do. Maybe this is just easier done than said. Initially, there's no force. It ain't stretched. At the very end, there's the big stretch. Add them together, divide by 2, and multiply by x. That's 1/2 kx times x. Well, you guys have already seen this. In one place or another, at one time or another, you've already seen this, or you're close to seeing this. You're going to see it eventually. Because you had taken the integral from 0 to x, the integral from 0 to x of the function kx dx. At the end of the day, you got 1/2 kx squared evaluated between the two here. I don't want to get into all the aesthetics of this, you guys. You know, you could have done this, could have done the other stuff. Doesn't really matter. In this particular case, there's ways to get around this. No doubt, there's ways to get around this. But you got this. So what's going on here? What just happened here? Well, I'm just saying somehow that spring got stretched. And since my hand didn't do it, when I was my hand didn't do it, the pulley didn't do it, the machine did. What did it? Well, I tell you what, we managed to heat up the gas. We were increasing the average kinetic energy per particle continuously. There was a lot of particles in there, capital N amount of particles in there, small n amount of moles in there, both indicative of the same amount of particles that are there. One's in moles and one's in flat out number of particles there. There's a lot of particles in there, and the average kinetic energy of the particles has been increased. As it's increasing, the collisions against the piston are going to be more frequent, more violent, and they're going to punch that thing out. It's going to come out of there. There will be a point, if you leave the temperature, if you finally stop at some temperature, it's going to stop right there, and that's where the piston is. The spring is pulling as hard as it can, and the gas is pushing against the spring is pulling against the piston to not let it go any further, and the gas is pushing against the piston to make it go further, but it can't make it go further. There is a point where the amount of force associated with the pressure of the gas at a particular temperature, that force is equal and opposite to the force of the spring. Well, okay, there's a lot going on here. So, just trying to. Again. I have this in more detail in the writing in Canvas. I don't kind of argue with myself how much of this I want to show. Don't want to get absolutely too redundant with it, but let's see what we can say. Well, I'll tell you, again, the pressure at a certain point associated with the violence of the collisions, I guess, is going to be such that there's going to be a force that's being exerted by these collisions. That force is equal and opposite to how the spring is pushing. So, we could say a lot. Now, I mean, basically you could say, I guess if you're talking about the piston being picked up, and so we try to, some places are better it's better to look at this in some places than others, right? But if you've got, and there's the piston, and there's the spring, and there is, there's the force, there's a force here and there's a force there. They're equal and opposite and it ain't moving. This force pulling down at a height, let's say this is the height D, you move through a height D. You started at 0. This thing started way down here. There's nothing here. It moved a distance x equal to D. Well, if x was equal to D, you could say, okay, let's, even in terms of just looking at the integral, I guess, go here. Go there. So there's a lot of ways. Okay, that's just, the D and the X are one and the same. That's not really an issue. And then the pressure's here. Well, what's going on here? Then we say pressure was force divided by area. So the force here, then we say force divided by area is pressure. So pressure is force divided by area. I do not know what my chalk is doing. It's breaking left and right on me here. Pressure is force divided by area. Force is pressure times area. This is all right. Let's try this again. Yeah. If pressure equals force divided by area, force equals pressure times area. So force equals pressure times area. Yeah. If that's the case, and this guy right here, the force is KD. At the very top, it's KD. The lower this spring would go, if you drop the temperature, the force ain't going to be as much. The KD, D's going to be a smaller number. D's going to be a smaller number, so the force ain't going to be as much. Well, the area don't change, but the pressure gets smaller. Notice you started at, the only way this is working, ladies and gentlemen, is down here the pressure's 0, up here the pressure's P. P max, we'll call it P max, that's equal to P. P here, P equals 0 or P equals P, right up here. Okay. So what's going on here? Well, we already kind of talked about this a little bit. So let me see where I can go. Some things are going to stay, some are going to go, I guess. All of this goes eventually, but let's see what we got. Yeah, like I said, we essentially talked about the forces being equal. Yeah, that's why the piston ain't moving at some point with the spring, let's say. And that's, or if you want to remove the because of the spring, the piston ain't moving. If you want to remove the spring, you got to put some other restraint on it for it not to pop out. Okay, for that particular temperature that's there. So force equals force. Okay, we said that KD equals PA. True. And we said a whole bunch of stuff there. Now, didn't we say there's a number of ways we could say it here. Now, the way I said it, I'm just kind of debating with myself when to kind of put this to you guys. This is fine. Yeah, there's so many ways to look at it. And like I said, I showed a bunch, little different language in different places in the same article that I put up in Canvas. Said it in different ways. All of them say the same thing. Were they all necessary? I don't know. You can argue a whole bunch of stuff, guys. Just trying to debate with myself which way is the best way to write this. They're all going basically in the same direction, guys. It might just be a horse apiece on this one. Let's see what I can say here. Yeah, well, this is at the very top. In a sense, this is like an F max and an F max, a maximum force. There is a maximum pressure at the top. There's a maximum distance. You know, you're saying basically KD equals PA. P is the biggest pressure at the very top when this thing can't push any harder to make this guy stretch more. When this guy has stretched as much as it can, and now it's so strong it's pulling back, but it can't get back because the pressure times the area is just as strong when the two forces are equal. That's what I was trying to say right here, you guys. It's essentially what I'm saying right there. Okay, for these two guys. You had a force this way, and you had a force that way. And that's the way to look at it. Now, let's kind of go. Now, again, we can resort to calculus and get the answers that we want to get. We also know we can get away because it's a linear equation. We can use algebra and we're fine. It works out just great. Tell you what. We've already kind of said this. Let's just say it again, I guess. I mean, I've written in kind of different language, so to speak. Force average, the average force in this whole process. Notice when you're first making this thing rise from the very bottom, there ain't a lot of force needed to make the spring stretch. The spring's not that strong down here. The more you stretch it, if it's an ideal spring, or the more that you compress it for that matter, that's another issue in itself. They use both with ideal springs when we're talking about oscillatory motion. For our purposes right now, we're not going there. We're just talking about something stretching. And we'll say the more you stretch this thing, the more force it is exerting to prevent you from stretching it. You stretched it a meter? Okay, that wasn't easy. When you're holding it at a meter, you got to hold a certain amount of force for that thing not to want to fly back, not to come back. You stretched it a meter. You stretched it 3 meters, 3 times the force that spring is exerting. 3 times the force it was exerting at 1 meter stretch, it's now exerting at 3 meter stretch. Stretch it to 30 meters. That's 10 times more what it was at the 3 meter stretch. It is 30 times more force it's exerting at 30 meter stretch as it was exerting at 1 meter stretch. And 10 times more force at 30 meter stretch is occurring. 10 times more force of not letting you go pull it further. You got to hold it with 10 times more force at 30 meter stretch than you were holding it at 3 meter stretch. And you got to hold it with 30 times more force at 30 meter stretch than you held it at 1 meter stretch. So it's a linear phenomenon. What does that mean? That means it's hard to move this thing. It's easy initially and it keeps getting harder. So it's not a constant force that you exert. It's a real light force early on and a very heavy force later on, and because it's a linear function, you can average the high and the low and that gets you there. You don't have to use calculus here. Technically, you should always use calculus, but we don't have to. You know, at least to kind of verify what's happening here. This is a special case that the calculus answer would give you the exact same answer as the algebraic look to it. It's a special case where it just becomes a simple algebra problem. What are we talking about? How much work did this get? Here's the big question. This is the real big question. We started this thing, the piston, so to speak. You know, here's the piston, and you know it started down here, and it worked its way this way. How far? That way. How much work had to be done on the gas? Well, it's kind of that's a little bit of a loaded statement. In essence, you're increasing the temperature. How did you increase the temperature? You did work, some kind of work. You put energy. Works kind of a loaded statement, guys. You put energy into the gas. You increased its internal energy. What was the internal energy of the gas at absolute temperature 0? At absolute temperature equal to 0, there's no molecular vibration, rotation, or translational motion. There is no kinetic energy whatsoever, vibrational, rotational, translational, none. Theoretically, if it was there at absolute 0, the internal energy of the gas is 0. Great. Why is that great? Because I started at 0. It's easy to count if you start at 0. When you put a temperature T when you increase that amount of matter, which is the gas, when you increase the average kinetic energy of its particles, you have increased its thermal energy. Really? Well, you've increased it from 0 thermal energy to some amount of thermal energy. Having done so, that increase in thermal energy means more violent collisions against the piston, which means it's capable of stretching the spring. The more violent the collisions, violent collisions are associated with great temperature. The great temperature will make that thing stretch even more. It'll give it a big pressure and a big volume. Remember I said earlier, PV equals nRT. And if P and V are big, you better believe the temperature is huge. According to the ideal gas law. So this thing, man, you got it up to here. Really? You did not add particles in here. The particles were already there, but they weren't moving. And I mean they really weren't moving theoretically. No vibrational motion, no rotational motion, no translational motion whatsoever. 0 kinetic energy total. If you add all the kinetic energy, that means 0 internal energy total. For our purposes in this discussion, using this language. You increase the temperature, it goes up. Yeah, the collisions are starting. You now have changed the internal energy of the system. I'd like to measure that. Well, that's why I put the spring in there, to be honest with you. Sort of. The hypothetical spring's in there to get us there. I want to know how much work was done by you heating this thing up from T equals 0, from T equals absolute 0. No internal energy in the gas at that moment. From T equals absolute 0, no internal energy in the gas at that moment, to some temperature T. Well, work got done, maybe I can figure it out. We already kind of know that, hey man, the bigger the temperature, the more the stretch. Yeah, that makes sense. You know, this thing would be way up here. You know, if you want to keep going, I don't want to ruin this, man, but up here. Keep drawing this thing, I could draw it up there onto the bricks. The more the temperature, the more the stretch for this ideal spring. Okay, we get all that. Still not quite the answers we want to get, but we get that. So what are we talking? Well, let's just see what kind of work was done, and maybe we can talk a little bit. Work is F average times D. And didn't we say, okay, we've been there, like I said, in the writing, writing on canvas, I write this about 3 or 4 times, guys. Forgive me. I mean, you might want to, hopefully it helps. Different looks at it. Maybe the repetition is the mother of learning, I guess you could say sometimes. So what do you got here? You got this. What's the average? Well, there's no force down here. There's nobody. That's to move the spring just a little bit. Right at the beginning, it's barely anything. In the beginning, there is no force fighting you. As soon as you move it, there's a force wanting to pull you back, which means you got to be strong enough to hold it there. And you got to be strong enough to keep pulling it if you want this thing to keep moving. And the more you pull it, the more it's pulling back at you. So the more work you got to do to get this thing to move from here to here, the more work you got to do. By the way, when D gets bigger, ladies and gentlemen, the volume gets bigger. If D is 1 meter, there's a volume V. If D is 10 meters, there's a volume 10V. Because the area of the piston doesn't change. There's a lot of ways we could look at this. We could say a lot of what ifs here. Let's not go there. We could still get through it, but it takes much longer than what we're going to do. It works. Whatever you want to do, it works. We can make it work. In the meantime, let's look at this. We can make it work. For now, let's just keep it kind of simple. The area here, the area of the piston is A. That ain't changing. A times D is the volume. If you increase D, you're increasing the volume. If you triple the distance D, you have tripled the volume. I mean, if volume equals A times D, then A times an elongation 3 times what it was initially of the spring, which means climb 3 times the height. That's, just pull the 3 out of there. That's 3AD. Yeah, didn't we just say AD though was V? Here's AD. That's equal to V. If you triple it, you triple V. Is there a moral to the story? Yeah, I don't want to make it sound like it's, I want to bother you too much on this. If you triple the distance, you're tripling the volume. If you make the distance 10 times what it was before, the volume's 10 times what it was before. So there's something going on here. There's a volume component to this whole thing too. All right, maybe this is just more easier done than said. Initially, when the piston's at the very bottom, it's 0. The force. At the very top, it's KD. Because KX is the force associated with the piston. So that's that. Let's average the high and the low. Let's average the high and the low. Add the high, add the low, divide by 2, then multiply by D. This is the average force, ladies and gentlemen. Multiply it by D. Okay. Absolutely, we know that. True. Is there a way we can interpret this in another manner? Well, first of all, that's true. And secondly, we've already delivered that speech. That's also true. So let's see what we can say here. This is kind of the crux of the whole thing. Let me see what... Look at that carefully. Because we're going to make the move there. So let's see here. going on here? Didn't we just say this? 0 is 0. That's not changing. KD is PA. P is the maximum pressure. You understand there's no pressure down here. When the absolute temperature is 0, when it's 0 degrees Kelvin, there is no pressure here. When you increase the when you got 0 degrees Kelvin, there is no temperature. I'm sorry, when you got 0 degrees absolute value temperature, that is absolute 0, and there's no pressure. When you increase the temperature, the pressure increases because there are collisions that are literally taking, and we talked about those collisions. We derived that when we talked about the kinetic theory of gases. We already derived that. Again, it depends when you're looking at it, the particular video. We have already been there. You'll see it. If you haven't already seen it, you'll see it. We've looked at it. Surway's got brilliant coverage of it. Other books have brilliant coverage of it. And I basically copied what they were saying. Basically looked at their argument, and that's what I presented to you guys as well. So you see, if you haven't seen it, you're going to see it. F equals KD. F equals KD, yeah, it does. The maximum force is F equals KD. It's also equal to P times A. Isn't pressure, and these are equal. Equal and opposite. We already delivered that speech. So KD is PA divided by 2 times the distance D. That's equal to work. Yeah. Average force, right, P times A is force. That's the maximum force because it's here on top. It's here on top. That's the P right here. That's the P here too, but P0 right here. But this one's something different. Force over area times area is force. Pressure is force divided by area times area, that's force. P times A, maximum force, plus the initial force, which the spring exerts, which you have to overcome. 0. In the beginning, it's just 0. At the end, it's PA. The average of the two, 0 plus PA, the average of the two is 0 plus PA divided by 2 times D is W. W, do this, it's PA divided by 2. It's 1/2 PAD. Is equal to, we've already been down that road before, AD is V. That's the big move. That's how the whole thing plays. There's a number of looks at it. I wrote it in different ways. Doesn't matter how you get there. We're going to assume it's going to happen slowly enough that there's no, it's just going to slowly get up to the top and then come back down. But it's not, there's a lot of flexibility in the thought process here, guys. As we said, there's no force that spring exerts in the beginning. Why? There's no temperature, first of all. There's nobody pushing against that piston to stretch the spring. When the spring ain't stretched, there's no force. Why would there be a force if there's no collisions happening? How could there be collisions if it's absolute 0 and there's no vibrational motion, no rotational motion, and no translational motion? None of that whatsoever. The collisions are what give you the pressure. The pressure is what's going to move the piston. Initially it's not going to. The more that T increases, the more you are going to move it. How much more? I don't know. That spring's pretty strong. If you want to stretch that spring 100 meters up into the air, let's say we got this thing set up that we can do that. We can put temperature, we can do stuff with the amount of particles. Now, if there's a lot of particles in there, isn't that pretty tough to move a lot of particles? Yeah, the more things there are to move, the harder it is to move them. But you need a lot of particles to move that huge piston. If you do it with less particles, you're going to need more temperature. If you got half the number of particles, you're going to need double the temperature to make them move. Okay? I have to look at that exactly how I'm saying it, but we can look at the math. It should be about right. Yeah. I mean, you'll see when we actually write the stuff down. It's going to say a lot. So we said initially there's no pressure. There's no force. The other one at the very top is PA divided by 2. And you moved it over there. So it's got to be the average force. The work was equal to 1/2 PAD AD is volume. Wait a minute. Isn't PV equal to nRT? Yeah, that's a constant. R is a constant. The more particles you have, moles are particles, guys. No, they're not. Well, yeah, but they're a measure of particles. 10 moles is twice as many particles as 5 moles. So I guess there's a measuring stick there. It's a measuring stick of sorts. It's a measuring stick of sorts. That tells us about how much that stuff is. Okay. PV equals nRT, huh? Work that was done was 1/2 PV. That's 1/2 nRT. Wow, that's huge. In another video, I kind of stopped there a little bit, then when I corrected it later, but let me not, I sort of stopped there and I corrected it. Let me not talk too much about it. That is the work. That is the work. You say, hey, wait a minute. If that's the work, that must be the internal energy that you put into the gas. That must be the internal energy that you have added to the gas, because there was no internal energy initially. You know, the spring wasn't stretched. Particles weren't moving at all. No vibrational motion whatsoever, no rotational motion whatsoever, no translational motion. They weren't able to, absolute zero. Nothing's moving. Yeah, okay, yeah, that's the work I did. That must be the amount of, that's proportional to the change in internal energy. It certainly is. It certainly is. If you were to triple the amount of, if you were to triple the amount of moles present and quadruple the absolute value temperature, 3 times 4 is 12. 12 times more work was done. 12 times more kinetic energy. Let's say it another way, better way. If you were to triple the amount of moles and quadruple the absolute value temperature, 3 times 4 is 12, there would be a value 12 times the size. 3 times 4 is 12. 12 times more, not 12 times, more is not a good word. 12 times, though we all use it, 12 times the amount of internal energy exists if you have 3 times the moles and 4 times the absolute value temperature. If you made N 3 times bigger and you made T 4 times bigger, N is 3 times bigger, N is 3 times bigger, T is 4 times bigger, 3 times 4 is 12. 12 times greater, 12 times the size is the internal energy in that circumstance as it was before you tripled the amount of moles and quadrupled the average kinetic energy of the particles. In other words, you quadrupled the absolute value temperature. If you made this 3 times the moles and you made this 3 times the moles that it initially was and 4 times the absolute value temperature that it initially was, 3 times 4 is 12. 12 times more massive. 12 times the size. Not good words here, guys. 12 times the amount of internal energy is present after you tripled the number of moles and after you quadrupled the absolute value temperature. 3 times 4, 12 times 12 times as much internal energy. 12 times the internal energy is present in that situation as was initially present before you tripled the moles and quadrupled the temperature. 12 times. 12 times the internal energy and 12 times the work is done. Then you say to me, yeah, Jim, if you're saying that, we just said it. That must be the internal energy. It is directly proportional to the internal energy that you added, but it's not exactly equal to it. Because only 1/3 of the particles, on average, are colliding with the piston at any given time. The other 1/3 are colliding somewhere else, and the last 1/3 are also colliding somewhere other than the other two are colliding. 2/3 of the particles are colliding elsewhere on average. This work got done with only 1/3 of the particles on average making the collisions. Or all of the particles making the collisions, but on average 1/3 of the total kinetic energy is being applied. You can look at it either way. All of the particles are making the collisions, but only 1/3 of their kinetic energy is being utilized to accomplish this work, if all of them are working together. Or on average, 1/3 of the particles are directly hitting this thing and making straight out collisions. Straight out collisions, perfectly elastically. So 1/3 of the particles are accomplishing this at any given time, or all of the particles are accomplishing this, but only 1/3 of their kinetic energy at a given period of time is being used. So only 1/3 of the total kinetic energy accomplished this. What does that mean? That means the total kinetic energy is 3 times that number, which means the internal energy is 3 times that number. Well, what's 3 times a half nRT? 3 times 1/2 nRT is 3/2 nRT. That sounds familiar. And that's how it works. And that's kind of how it works. Okay, I just said it. I got it written out there for you as well. Let me just try to... And we talked about, there's a lot of ways to go. We already talked about this in other circumstances. We've already talked about this, and the degrees of freedom, in this case, it's a monatomic ideal gas, so all the degrees of freedom are, they're just, it's partitioned between the 3 of them. Now, had this been some other, a diatomic gas, or some, things of that nature, we'd have to, there's other stuff we'd have to look to see what's going on here. I mean, but basically, every degree of freedom has an association of 1/2 nRT. So 3 times, so just take the degrees of freedom and multiply by the 1/2 nRT. There's a lot more to this. It meets the eye, but I guess, to me, it's a good gut feeling way to look at this thing. I can't emphasize how closely intertwined pressure, volume, and temperature are, how they interact for a given system, for a given circumstance that we got. Notice, I didn't really care much about the spring, but the spring was kind of a measuring stick as to what was going on here. Let's get an idea what kind of work is getting done here, guys. So we said that, and that's the thing. That's the big thing. And like I said, if somebody said to you, hey, look, what's going on here, man? What are you talking about? Are you talking about, well, I can't emphasize how big this is. W equals 1/2 nRT. It doesn't matter if there's 7 degrees of freedom. 1/2 nRT is associated with what took place in association with 1 degree of freedom. There's 7 of them altogether, so 7 times 1/2 nRT is 1/2 nRT is associated with just 1 degree of freedom. What's going on in that 1 degree of freedom? What's going on with that 1 degree of freedom? Man, you just moved a piston with that 1 degree of freedom. Yeah, there's 7 degrees of freedom. Each one has 1/2 nRT. Oh, and there's 7 of them? 7 times 1/2 nRT is 7/2 nRT. So there, we could say a lot. For polyatomic molecules, from monatomic molecules to polyatomic molecules, when we talk about the degrees of freedom. It's a little bit of a gut feeling way to look at it. Just state what I've already just said right here, guys. And we'll take it from there, I guess. It's one way to kind of look at it. I mean, that spring, in a sense, is the strength of the container on all sides. Well, I just care about the one side because that's the one that actually could move. The other ones didn't get moved. And the degrees of freedom, what was going on, the other degrees of freedom, those didn't contribute. At any given instant, they did not contribute to that piston moving. On average, only 1/3 of the kinetic energy was contributing to the movement of the piston. So we kind of look. So let's take. I think I basically said it. Arguably, you don't need to say what I'm about to say, but let me say it anyway. It'd be nice if I could find all my erasers too. All right, here we go. Okay. So we basically said it. Let's talk a little bit. Let's just talk about it. So we just kind of said it. I mean, it's a horse apiece where you want to start with this thing sometimes, but let's see where we're going to go. We said that the work, I mean, there's so much to this, guys, that more than meets the eye. I mean, that's my chalk stayed in place, but okay, that's another issue. There's a lot here. There's a lot here. Yeah, pressure's a big thing. So is volume. If you want to get a great volume, there's a lot that has to happen. A lot of work's got to get done to get a great volume. A lot of pressure's got to be, if there's a lot of pressure at a great volume, man, a lot of work had to be done to get there. There's a lot of internal energy in that gas. It's directly proportional to the things I wrote down. It's just not exactly equal to them. It's like me saying to you, I took 1 cubic meter of water out of this lake, Lake Baikal, Lake Michigan, whatever. Took 1 cubic meter of water out of there, and it's 1,000 kilograms. It's a lot. It sure is. Therefore, that's the mass of Lake Baikal. No, but it's proportional to what the mass is. Because if I went to some other liquid and pulled out 1 cubic meter of some other liquid, and it only weighed 200 kilograms. It only had a mass of 200 kilograms, whereas the lake, that 1 cubic meter of water had 1,000 kilograms of mass. The other 1 cubic meter had only 200 kilograms of mass. The lake fluid, called water, is 5 times more massive than the other fluid. Yeah. For the same volume lake, a lake of water is 5 times more massive than the lake composed of that other fluid, if it's the same volume. Sure, they're proportional. That's kind of what we're saying here. What are they exactly? we said this. There's so much to this. I mean, so much to this. True. Yeah, I know. But you saw me earlier. I was jumping up and down saying, on average, that's only 1/3 of the total kinetic energy of the system that's making that happen. Well, you saw earlier, we actually found ETH to be 3/2 nRT, and that was equal to the total kinetic energy. Okay. Good enough for me. Okay. So what does that mean? Well, that means that if you take this and triple it, let's just take these two. Let me just go down the line here. Multiply this by 3. You got KE total. Multiply by 3, 3/2 nRT. There is that quantity. Multiply by 3 all the way across. Yeah, that's true. It's 3 times the W. Yeah, that's great. This is big. Didn't we say that KE was equal to that, though? Yeah, absolutely we did. ETH is KE total. Three-halves nRT for a monatomic ideal gas. Yeah, and I already told you by the equal partition theorem, by the principle of equal partition of energy, by the principle of equal partition of energy, ETH is number of degrees of freedom times 1/2 nRT. See, like that 1/2 nRT is pretty big. It is associated with each degree of freedom. We happened to see it when work was done, but only 1 degree of freedom, quote unquote, did that work, if you allow me to say that. Don't hold me to it in the strictest sense as far as the linguistics are concerned, but you know what I'm saying. What was associated, whatever energy is associated with 1 degree of freedom, that's the one associated with the work that was done in this idealized circumstance. 1/2 nRT is associated with 1 degree of freedom. However many degrees of freedom that you have, that's what you're going to multiply by 1/2 nRT. Very significant. Absolutely, guys. And there it is. We got it in the notes as well. Thank you for your time.